In this video, we'll do some examples finding areas between curves. So in the first example, let's find the area between y equals 12 minus x squared. Let's put a comma here. Y equals 3x plus 2 and x equals negative 1. For x greater than or equal to negative 1. Okay, so let's begin by drawing a picture. So I'll draw some axes. All right, let me draw the x-axis a little higher. So y equals 12 minus x squared. That is an upside down parabola. So it's a downward facing parabola. And I know that this y-intercept of it, if I were to plug in x equals 0, I'll get that the y value is 12. Okay, so that is, this equation is y equals 12 minus x squared. For y equals 3x plus 2, that's a line. Its y-intercept is 2. And the slope is positive 3. Okay, so it's an upward sloping line. So maybe that looks something like this. So y equals 3x plus 2. Notice that that crosses this parabola twice based off of our picture. Okay, and then we have this line, x equals negative 1. That's a vertical line. So negative 1 is somewhere over here. It's to the left of the x-intercept of that line. If we were to find the x-intercept of the line 3x plus 2, it turns out it's at negative 2/3. Okay, but now if I draw that vertical line at negative 1, it looks something like this. Okay, so looking at my picture, these three curves, they sort of create two regions. There's two regions that are bounded by both of them. So what is this question talking about? One, it tells us when it says, oh, x needs to be greater than or equal to negative 1. That means it is just talking about the region to the right of that vertical line, because that's the region where x is greater than or equal to negative 1. Okay, so when I set up my integral for this area, I need to know, well, what's the smallest x gets? And that seems to be negative 1. That's sort of going to be the left, cutoff. And the biggest x gets is at this intersection point. So I will need to figure out, well, what is that x value? So we will need to find that intersection point. So finding that intersection point. So we can get that if we take this parabola equation and that line equation, and we know what y equals for both of them, just set those equal. So we'll get 12 minus x squared equals 3x plus 2. And if we rearrange this, I can move all the terms to the right and get 0 equals x squared plus 3x minus 10. And now this is a quadratic, and this quadratic factors pretty easily. We get 0 equals x plus 5 times x minus 2. And from there we get that either x is negative 5 from the first parentheses or positive 2 from the second one. So looking at my picture, where is x equal to negative 5? Well, that would be at this intersection point. This is where x is going to be negative 5. But we care about the one where x is positive, and that was 2. So that's going to be the value of this other intersection point. Alrighty, so from here, we would be ready to set up an integral for our area. So our area, remember, the general formula is the area is going to go from a to b. We'll have our top function, which I call y subscript top, because we're going to use the formula with the y value isolated, which it already is, and then minus the bottom function, and then this is going to be a dx integral. So I can figure out the top function and the bottom function by looking at my picture. For this problem, I don't think it's too tricky, but I'm going to show you a way I could figure them out in general, which is I take, I draw a vertical line somewhere in my region, and when I do that, it hits a function at the top, and then it hits a function at the bottom. So the function hits on the top, that's my top function. The function it hits on the bottom is my bottom function. So no matter where I draw the vertical line in this picture, even if I were to draw it here, that top function stays as the parabola the whole way, and the bottom function stays as the line the whole way. We'll see some examples later where that either the top function or maybe the bottom function will change, and we'll see how to handle that later in those future examples. But for right now, it's the same the whole way. We could just set up an integral for this, and our integral will go from, because it's a dx integral, I need to know what's the smallest x could be, which is negative 1 for my region, and for the upper limit, what's the biggest it could be, which is 2. And then I do my top function, which was 12 minus x squared. That was my y subscript top. And then I do minus the bottom function. So I got to put a parentheses around this whole thing. So I remember it's minus all of this. Okay, and this is going to be the bottom function. And the bottom function was out of line. And y for the bottom function equaled 3x plus 2 dx. Okay. All right, and now we are ready to evaluate this. So we got the integral from -1 to 2. If I simplify this, we will end up getting, all right, negative x squared first. Then I'll do the minus 3x. We'll get 12 minus 2, which is plus 10 dx. All right, and now from here, we're ready to do this antiderivative. We'll get negative x to the third over 3 minus 3 halves x squared plus 10x. And then I got to evaluate this at 2 and -1. All right, so if I plug in 2 into this, we'll get negative, and then parentheses 2 cubed over 3 minus 3 halves in parentheses 2 squared, and then plus 10 times 2. All right, and then I got to do minus. Got to put a big old parentheses around this. Now I'm going to plug in -1. So I get minus -1 cubed over 3 minus 3 halves times -1 being squared plus 10 times -1. Close that parentheses. All right, so if I simplify, we get -8 thirds, and then minus 6 plus 20. We get minus, and in the parentheses, we'll have positive 1/3 minus 3 halves minus 10. All right, so if I take all the integers, so we got the minus 6, we got the plus 20, and then we'll get negative 10, which will become positive 10. That will end up being positive 24. If I take all the terms that have this 3 as a denominator, we have, let's see, we have minus 8 thirds, and then we'll get minus 1 thirds. So that'll be minus 9 over 3. All right, and then the other terms, well, let's see, there'll be a positive 3 halves. Okay, so 24, this is 24 minus 3, which is 21. Let's get a common denominator. 21 will become 42 over 2, plus 3 halves, and that is 45 over 2. And that's our answer. That is our area between those two curves. So when we find the area between two curves, the convention is that we want this area to be non-negative. So it matters which function I let be the top function, which function I let be the bottom function. It's got to be whichever one is higher up in the picture. That's the top function. All right, let's do another example. All right, so this time, let's find the area between y equals sine of x and y equals sine of 2x over the interval from 0 to pi. All right, so let's begin by drawing a picture. So I'm going to draw some axes. I'm just drawing mostly the region where x is positive because my interval is just from 0 to pi. Okay, so I'm going to begin by drawing the graph of sine x on that interval, and that'll look something like this. It'll reach a high point and then go down. So this is pi, and sine reaches its high point at pi over 2. That's when it reaches its high point. So this is the graph of y equals sine of x. For the graph of sine of 2x, having the 2x there doubles the frequency. So instead of sort of going up and down from 0 to pi, it'll do that from 0 to pi over 2. So it'll look more like, it'll reach the high point here, twice as quickly, and then go down and reach the x-axis at pi over 2. And then it'll reach its low point, and it'll make a full period, this is called, by the time I get to pi. Because sine x would have made a full period by the time I got to 2 pi, so sine of 2x does it sort of twice as fast, which is why it does one full oscillation by the time I get to pi. And of course the graph will keep going, but we mostly care about, well, what's happening on the interval from 0 to pi, because that's what our question is focused on. So if we look at this picture, let's find our intersection points. So I could figure out, well, what is that x value? Find the intersection points. But the reason I'm going to need to do that is, if I think about my top function and the bottom function, if I were to draw a vertical line somewhere here, The top function is the sine of 2x graph. In fact, let me label that. So the purple one, this is y equals sine of 2x. So over there, the top function is on the sine of 2x graph. The bottom function is sine of x. But if I draw a vertical line over here, the top and the bottom function change. The top function is now sine x, and the bottom function is sine of 2x. What that means is, if I'm trying to figure out this area, I'm trying to figure out the region bounded by the two curves, which is all of this. It is all of this. We are going to need to split it up into two integrals at this intersection point. Okay, so to find the intersection point, we will need to set sine of 2x equal to sine x. So to solve this, there's a key trig identity we'll need. So there's a trig identity for sine of 2x. So sine of 2x, recall, I gotta think back to pre-calc or trig here. This is equal to 2 sine x cosine x. All right, so if I substitute that in, we'll get 2 sine x cosine x on the left equals this sine x on the right. And now I don't want to just divide both sides by sine x, because if I divide both sides of an equation by a variable, I can lose answers. Instead, bring everything to one side. So I get 2 sine x cosine x minus sine x, so that the other side, bring everything to one side, so the other side equals 0. Then factor that term out. So I'll factor out the sine x, and I'm left with 2 cosine x minus 1. Okay, now from here it's not going to be too bad. I get, from the sine x term, I get sine x equals 0. Or from this cosine portion, I get cosine x could be equal to 1/2. So when is sine x equal to 0? So on our interval from 0 to pi, this just happens when x is 0 and pi. And what about cosine x being equal to 1/2? Well, on our interval from 0 to pi, that only happens when x is pi over 3. So I'm using my previous knowledge about the unit circle. Okay, so now we know where this point is. This one happens to be at pi over 3. The other intersection points that we got at 0 and pi, those were here and here. Okay, so I'm going to call this first region A1 and this second region A2. So if we want the area, we got to add up the area of A1 plus the area of A2. So for A1, looking at my picture, my integral, if I think about my x values, they go from 0 to pi over 3, and the top function is sine of 2x. So I go integral from 0 to pi over 3. The top function is sine of 2x. And then minus the bottom function was sine of x for that region. And then I write dx. And then for my second integral, the x values start at pi over 3, and they go until pi. So pi over 3 until pi. And the top function was sine of x, because it switches now. And then minus the bottom function is sine of 2x dx. Okay, so we've at this point, I think, done the hard part, which is setting up the integral. Identifying what is the top function, what is the bottom function, why do I need to split it up? It's because the top and the bottom function switch at some point. Okay, now we're ready to do antiderivatives. So for sine of 2x, that antiderivative is going to be, we'll get negative 1/2 cosine of 2x. And I need the negative 1/2 because if I do a check and I take the derivative of this, the derivative of cosine of 2x will be negative sine of 2x times 2 when I do the derivative of the inside because of the chain rule. Okay, so the dividing by this 2 will sort of cancel out what happens if I were to do the derivative with the chain rule. Okay, so for negative sine x, that antiderivative will be just plus cosine. Okay, so with this, we now got to plug in 0 and pi over 3. And then plus for the next term, antiderivative of sine is negative cosine. And then for minus sine 2x, we'll get plus 1/2 cosine of 2x. Vertical line to indicate I got to plug in pi over 3 and pi. Okay, so plugging pi over 3 into this, I get negative 1/2 cosine of 2 pi over 3 plus cosine of pi over 3. And then I have to have minus, I'll put a big parentheses. Now I plug in 0 into this. So I get negative 1/2 cosine of 0 plus cosine of 0. All right, and then I have plus. Now I'm going to plug in pi into my terms. So I'll get, let's see, I'll get negative cosine of pi plus 1/2 cosine of 2 pi. Close that. And then I got to do minus what I get when I plug in pi over 3. So that'll give me negative cosine of pi over 3. And then plus 1/2. 1/2 cosine of 2 pi over 3. All right, so simplifying this, we end up getting, this will be negative 1/2. That cosine of 2 pi over 3 is also negative 1/2. Plus cosine of pi over 3 is positive 1/2. And then I get minus, inside of this parentheses, we will have negative 1/2, because cosine of 0 is 1, and then plus 1. And then plus going to the next bracket, cosine of pi is negative 1, so this will become positive 1, because the other negative in front of it. Cosine of 2 pi is 1, so I get plus 1/2. And then we get minus the stuff in this last bracket. So I'll get negative 1/2 plus 1/2 times negative 1/2, because that's cosine of 2 pi over 3. So from here, it's just some basic arithmetic. So I'm just going to write dot, dot, dot. It's just 1 or 2 lines of basic arithmetic. And what you end up getting is 5/2. So I'm leaving that arithmetic for you to verify. So in terms of our goals for this section, we finished goal 2, doing examples finding the area between curves. So in the next video, we'll look at situations where our equations aren't always given in the form y equals some stuff. Sometimes they're given in the form x equals some stuff. And in those situations, it may make more sense to think about our area in a different way.